So, well, let me start from the beginning. We want to solve the Schrödinger equation, and as Mario pointed out, this has various aspects of it. It has the if you go down the Bonomo approximation, one aspect is solving the electronic Schrödinger equation. But recently I've gained interest. It's a fact, it's maybe not so recent anyway, but increasing interest in solving nuclear Schrödinger equation, either for for finding bound vibrational state or for solving for time-dependent dynamics. And if you look at it to proceed this way, you have if you want this sort of complete solution to the problem, you need to solve not only the electronic structure method, for which there's many different methods available, but you also need to find a way to get potential, because that appears in either these nuclear Schrödinger equations, such that you eventually be able to solve the nuclear Schrödinger equation, which is, by the way, a problem in itself. I'm not going to talk so much about the third one, but I just want to point out sort of that, it maybe has been the traditional wisdom that if you solve the nuclear Schrödinger equation, it's very complicated and exact methods are limited to maybe a few dimensional problems like 6 dimension and so on, and we are not there anymore. So let me outline first, sort of in time-independent computations. Indeed, we have developed vibrational couple cluster methods, and we have developed then hierarchies of vibrational couple cluster methods, such that when you consider a molecule, this is looking at ethylene fundamentals on the error, average error at different excitation level, and we then see convergence. You have this convergence both for a more standard linear parameterization, but in particular, you have it for the couple cluster. Now, the advantage of the couple cluster is that it's your better convergence, but it's also size consistent, that you can hope this to be applicable to large molecules. Now, this wouldn't be useful unless you could actually make it run for larger molecules, and this is just what the other side of this shows here, because here you have sort of computational time versus number of modes, for polyaromatic hydrocarbons of increasing number of modes. And indeed, the computational cost increases, maybe more than we would like, but it's still only sort of some polynomial order. Here is m to the third for a couple cluster with signal and doubles in it. And higher order couple cluster will have higher order scalar, so they would be more costly. On the other side, as we can improve efficiency by tensor methods and by looking at truncating couplings with decaying as due to the expected decay of importance over distance and so on. So this is very much in progress. We are definitely not limited to sort of a hard limit in size. Doesn't mean that it's not challenging. This was for time-independent computations. We are also found very interested in recent years here to try to aim for the time-dependent problems. And one of the golden standard here is the multi-configuration time-dependent hardware methods. We are also sort of developing our own second quantization framework, such that we could develop sort of truncated versions. And here is an example of what we call multi-configuration truncated time-dependent hardware, looking for transition state flux of the system here. Again, this is a not completely smallish system, and we can compute it in with all the degrees of freedom. We're also looking at time-dependent vibrational couple cluster theory to do the same, very much work in development. Again, here's the sort of the computation time scaling. Again, you can do that with third order scaling, and it has the same advantage as mentioned before versus the linear, relative to more standard linear expansion in configuration space. Now, in fact, this was not so much this I want to talk about, because that is per se, these problems, let's say, are not employing what I would call machine learning methods, but they all they're only relevant to the extent that you actually can obtain and construct potential energy surfaces that make these computations relevant. So in our work, which is then based on developing and concretely this program, MIDAS program that has this time-dependent wave function methods in it, they they need a Hamiltonian, and the core is that we need to have a representation of the Hamiltonian in some form, and then that is then the task of finding, in particular, the potential energy of surface. Kinetic energy is, in fact, also a bit of an issue, but that's not going to be discussed today. And here we sort of consider that like a potential energy constructor. We have sort of methods which calls electronic structure programs automatically to finally spit out Hamiltonian in a form that's convenient for the dynamics. And this is this sum over product form. So it's a sum of products where this MT is simply a set of modes that is active for a given term. So this is a very general form, but of course it's still a specific mathematical choice that is convenient for wave function, meaning in the nuclear wave function computations, because you can kind of, every term you can apply this one mode operator at a time and so on. And that's important for their efficiency. But if you go into the potential energy business, of course, we would say that if I'm able to, by various advanced electronic structure methods, to compute points, I could just compute enough of them. That would be easy in one dimensional. But as we go to higher dimensions, we have the issue that if I have G points per dimension and I have capital M dimension, I would have this exponential scaling. So we need to do something about that. So here comes some steps. One first is we do kind of a mode expansion, or many mode expansion, n mode expansion, incremental, cluster, cut HDMR. Same idea has arisen in different contexts. So we consider and kind of an expansion of the potential that you are sure is going to converge, but you consider one mode at a time, the sum over all one modes, and then you have corrections from 2-mode couplings and 3-mode couplings and so on. In general, I will then write the potential as a sum over mode couplings, where this M here is just the vector of the indices that are active in a particular couple. So this full potential becomes a sum over small potentials. And if you now truncate this, you go from the exponential scaling down to a, let's say, polynomial scaling in G, depending on your cutoff. This is still potentially a lot of single computations to get information on the potential. This is what we want to deduce. Once you have got this one, you can, for each of these small functions here, you can fit those to a sum by having some fit basis, and then you eventually get your sum of products Hamiltonian. So that's all kind of like the technical fitting issues. Most important is, how do we find the points? How do we select points? And you can say, then I can, as a human, know the concrete problem. I could maybe sit and think and define a grid. And we call this a static grid approach. Ultimately, I think that will be very human time consuming, and might also risk of being computationally expensive or error prone. Rather, we prefer to try to make it into an iterative approach, where we would like to iteratively build the potential. And here is also very specific for what we are doing is that we want to build the potential energy surface of a given molecule. We do not pretend that we will generate any kind of global force field at this stage, at least. So the point is, we want to have the potential to use it in the nuclear dynamics. So it's kind of a step on the way. So we want to build that in. So we're not only interested in the PES, but actually we're maybe more interested in the final wave function and energies of the nuclear problem. We have developed an iterative approach to address this, called adaptive density guided approach. So what we do there is we use densities of the nuclear wave function, the one mode densities to make it concrete and simple. And we use that to find the boundaries and the grid mesh, and in general decide how to do it. Now, some may think that now sort of we go a bit in a circle, it bites its own tail, because I am wanting to use the one mode density to find the potential. But clearly, to get those densities, I need the potential. So it is a bit biting its own tail. So what I want to show now is that we can actually do this very efficiently. We're using the vibrational self-consistent field. It's a well-known scheme. I don't have anything new to add, except that we have made a more recent implementation that's extremely fast. So the idea is you have the wave functions, the sum of products. You do a variation principle to find the one mode functions of this project. Thereby it becomes, let's say, a product function with anharmonic one mode functions for every sort of state you represent by VSF. You require variation principle, and this gives you sort of a mean field equation. So very much like Hartree-Fock self-consistent field, there's no exchange because we treat modes as distinguishable. you can do these computations with a sum of product Hamiltonian in a fraction of a second. So by using this, we have a fast way for a given potential to get these one-mode functions and thereby densities of those. So what we do in this AdGPI approach is that we generate a density. Now you're typically interested in not only one state, but more like a set of lower states. So we do an averaging, and we have an average density, which is also nice because it doesn't have sort of complete as oscillatory as one particular excited state, but kind of like in shape, something like given in this picture. And then what we do is that we are interested in getting the potential where there's significant densities. So what we will iterate on in AdGPI, determine iterative, is the potential such that these integrals of the potential over the density in intervals become stable. So AdGPI is a change algorithm. You do changes and then you see you converge. I have a little cartoon here showing how it works. So let's say we start with something, takes 3 points. We do take these 3 points and we make a fit. This is not too hard. I'm sorry if it doesn't look so nice. Maybe it's bad fit. But anyway, you get the idea. This is a cartoon. So we have 3 points. We have a fit. With this fit, we can actually compute this density, the average density. We can then say, okay, is this good? Well, this is the initial state. So there's nothing I can do yet to qualify it good, but I can try to make a further change and see what happens. So what I do now is I can compute these test quantities in these intervals of choice. So I will now subdivide my intervals and then compute this test quantity before I do a computation. Now I will then do a computation here. So these are the new blue points. I will then fit my function potential here, and I will compute my new density as computed in this one here. And now I can compare this test quantity with what I have now with what I have before. So this gives a sort of a physical test. Is this potential that we're having, is that about to be converged now? Is it changing significantly? If it is changing significantly, I should add further points. If not, I will not add more. So if you continue, you will see that here we kind of conclude that over to the one side we are converged, but the other sides we are not. So we will do further subdivisions and try new points, new fitting, new density computation, and so on. What about the boundaries? Well, the boundaries we determine them so that we have no leaking of the wave function. This is very important. If you have leaking of wave function to high extent beyond the boundaries of your computations, you have the risk of extrapolating your potential too much, which can be not so nice for variational computations of nuclear motion. In higher dimension, it's a bit the same story, except of course you take sort of a kind of a direct product of it and investigate these sort of boxes instead of the intervals. So that goes to increasing higher dimensionality. This is good in the sense that you do not have to, let's say like here, subdivide in all boxes, but still there's kind of like the usual direct product problem of direct products, right? You get some increase of it. Okay, so in summary, adaptive density guided approach was something we developed over the years and used in various contexts. I think it was carried out and implemented without thinking in terms of machine learning, but you could say it's kind of like a physical-based active learning. We use some physics and some analysis there to decide what points to pick out to eventually represent this function that we are including. And then at the end of the day, we then fit the result to a form we like. So we have a mathematical representation of the potential and the Hamiltonian operator. Now we can sort of augment that with another approach more directly into machine learning. Now this is maybe, I can do this fast because already Marcus Hayek talked about the Gaussian process regression, and everybody should realize that Gaussian process regression as such is not a new with me or anything like that. It's a well-known method, and the only thing is here we apply it in this context here to boost this AdGPI-based potential energy surface generation. So the idea is that if you have a set of data points X and you want to predict new function values V star, here you assume they have a joint probabilities distribution, so you can have new data points predicted given the on condition on the observed points. And here you then have the sort of standard GPR equations for the mean and the probability, or let's say we'll say covariance matrix, which I use then as the variance of the prediction, which is then in particular was Marcus Reyer stressed, and also in his use, is like tells us something about how good are our estimates at a given point with the given data we have at this moment. It depends on things, because in here you have a kernel matrix, the covariance matrix. You need some choices. There needs to be some hyperparameters. We are optimizing those by maximizing likelihood, standard procedure. Gaussian kernel is smooth one, so it ensures smoothness, differentiability of the function. We have also extended to include gradients and Hessians and stuff like that. We use internal coordinates because that's a good thing to do for potential energy surfaces. But let's see. So, and here is sort of a cartoon that sort of illustrates, what is the idea as you find that you add points on something that's very suggestive, like looks like Morse oscillator. You have that the wilderness of potential functions in which you could be sampling from your Gaussian distribution. You have a confidence interval, and that shrinks where you have data and is still very undetermined outside your range of data. So again, where you extrapolate is a little bit more dangerous. Okay, but still, you have a confidence interval, and we can do predictions with it. The first step we're going to combine it with is AdGPI. Is we're using AdGPI to generate grids in lower dimension, and then we use this GPR to do kind of an interpolation. We can call it interpolation / extrapolation. See, if you have a 1D cut here, and you have points here and here, actually, you might take the risk of trying to predict something out here in the 2-dimensional space. And even more relevant, if you're having a 3D picture, if you are testing these one and have a good physical grid, you are actually learning a lot about the function, and you can try to make a guess on what is out there. In particular, you could do that if you combine it with delta learning methods. So you learn the high precision data, let's say along the faces of the cube here, and then you have a cheap method, and then learning the difference between the expensive and the cheap method, and you can think here in our concepts explicitly correlated coupled cluster methods and things like HOT2FOG or MP2, which is much faster. So then we have an algorithm that goes like this. You run AdGPI, and you have it in a switch. If you have a low mode coupling level, you will actually be solving real electronic structure computations, and we do the usual AdGPI iterations here. But at some point, you sort of go to a higher coupling level. Let's say you go from 2 to 3 mode couplings, and then you choose to, sorry, there's something teasing me all the time here. Then you switch instead to do not actual prediction. We simply do the GPR predictions, where the GPR is then based on the database you have. So, and that's for the delta, and then you add sort of the energy of the lower level method. And here's sort of figure how it performs for a bunch of smallish molecules. And if you and this is this is a spectroscopy game, so this is a game about reciproc centimeter accuracy, so depending on the eye, you see what you think about accuracy here, but the broad distributions here tend to be those that come from 1D to 2D, and the 2Ds are so important that you do not predict those with what I would say very high accuracy. But if you go to the 2 to 3D extrapolation, so you actually only generate a high precision grid in for the 2 dimensions, let's say 2 mode couplings, you can actually quite accurately predict the result in the 3 mode, what you would actually have obtained in a full 3 mode computations with this. When I say 2 mode and 3 mode, it's important to stress that this is the coupling level. We have a full dimensionality model. This is not so important for these ones, but even if you go to higher system, right, 2 mode means just I have only pair potential. 3 mode means I have 1, 2, and 3 mode couplings, but I have all the 1, 2, and 3 mode couplings. Okay, but this was sort of just running AdGPI and then stepping further. But we can also sort of build it more into the machine of AdGPI, which we have done more recently. So here we have the thing, we still have this AdGPI, which calls for points, but it calls first to the GPR So we use the GPR as a sort of a surrogate for electronic structure computations. And if needed, the GPR will then call for electronic structure points that will return to the GPR, extend its database, and eventually then use that in the AdGPI, which as usual take care of delivering the Hamiltonian in formula I can use for my phi dynamics. So in this way, we want to combine AdGPI for the physical relevant point. We want to use the GPR for the statistical analysis. Okay, and how do we do that? Here's a small argument. If again, in the spirit of AdGPI, I would say, what is the error of the potential? Well, if I have an error in the potential, I could estimate like a density times error in potential. The error in potential also will affect the density, but still as a rough estimate. I could then make my sum into remote couplings, and then I would have these small these errors in these subpotentials. I say that this is then an integral of this thing, and I can try to make to subdivide that further into sort of boxes. And here's a kind of boxing. Here you have a two-dimensional things, and by boxing I might just mean the four different, let's say, different errors divided by the axis here, for example, for let's say plus and minus direction. And then I could say that these integrals in these different boxes are smaller than the size of the box times the maximum value in here. This is a very rough estimate, and I don't use that in the computations as such, except I use this to motivate why, if I consider like an error, let's say an estimate of let's say uncertainty for a given point that I try to predict with GPR, should I switch this to become an electronic structure point or not? Then that is something to do with the error of this box times the density, the maximum density in the box, or let's say at the point of view of the maximum point, and let's say the variance at this point again. So this is where the variance of GPR is used. Then we have the AdGPI algorithm, which runs sort of double iterative. So outermost, you have a loop over GPR iterations, and that relates to you take a database, you do GPR on the GPR that's done with this database. So here, and with that AdGPI, you generate a set of grid points. You can see it in the figure below here. You actually will, with the blue one as an example, you generate a lot of points, and for those points you get out energies, which you use inside the AdGPI, but you also get out the variance, which is what is given here. Now, when you have done with such a computation, we take all this set of data points are not really computed by electronic structure, they are computed by GPR predictions, but then you can go and investigate this test quantities here and try to make a short list of computations that you want to switch to actually become electronic structure. And that we do in this following way. We have a threshold for this test quantity, and if it's larger, it's a candidate. However, we add only a little bit at a time, and this is where the boxing come in. We only add a maximum amount for each box, and that is limited in essence to 1. And the idea is here, if you have an area where you're very uncertain, you may want to request a lot of points out here, but it may be smart not to add them all at one time, but only at one, and see how things improve. And then a later round we'll have to add if more are needed. And finally, to avoid extrapolation, you also ensure that in the one-way part, you always pick the end point, because the density will decay, but it's risky still to do the extrapolation. So this is why in this cartoon here, you will see the endpoint has been selected in this first iteration, and then subsequent iteration. Now the variance has become very small, but of course it still sort of depends on uncertainty you assign to individual points. But in that regard, the next set AdGPI will have this set of points, and then we pick the next one is the black one. And as in this way, you will decay the variance in the function. You will be learning it to a sufficient degree, and eventually it will not matter so much anymore. So this setup will run until convergence. In 2D, it looks like this, where you can see the uncertainty, the variance again. So it's very uncertain in iteration 1, but as we proceed with iteration, it becomes blue, meaning the variance becomes smaller. This is done by placing points. The green ones are sort of the newly added points. So the green one here is this point that it will select in computing the next one in iteration 1, and then new green points will be appearing. The reason why it has this funny shape is due to that the additional point is weighted by the density. So The density weighting ensures that makes us pick not the corner points first, because they might be very well the most one with the highest variance, but it's weighted with the importance weighting from the nuclear waveforms related to what we want to use it for. So what we do get out of that is that we can get a reduced number of points, a significant factor. Typically it's something we can reduce by, let's say, 50 to 95% of root mean square in a bunch of small molecules, about 80% or 70 in these cases here. So 70, 80% a bit on what you mean. It means you can get by with, let's say, 1/4 of the data or something like that. The accuracy is reasonably high. We are talking errors in various ways down to a few reciproc centimeter. And I have to say that it will be hard to control, to be sure you have a cup cluster that's accurate, more accurate than this. It will even be hard to have control over all numerical issues to the same, a lot of tiny issues will appear down in the 0 point something regime. So this is pretty good. Here is an error distribution. I just want to point out that we have to assign, say, an uncertainty to the individual point. If you go too uncertain, if you don't trust your own data too much, you will actually get a poor prediction. That's perhaps not so surprising. So you want to balance that in some way. So you want to assign some small uncertainty, and you might use this trick of heterozygotic different uncertainties. And you also don't want to make it come 0, because then it becomes numerically more tricky. So we get a reduction in the number of data points. And how does that occur about? You can have one insight is that I talked about the number of points per dimension. And here it is, you see for AdGPI, for 1 dimension, you have about 22, and 2 dimension 11 and 5. What happens? And that is already great with AdGPI, that AdGPI traces that most 2 and 3 mode couplings are on average less important. So you can get by with smaller points. That is one we gain by AdGPI. But the GPR AdGPI, in addition, reduces these numbers significantly, 1 mode down to 5, 4, 3 type of things. So these are really small number of data points. Okay, so I'm actually
sorry to interrupt, but you're really running out of time.
Yes, so I jumped to the summary. Sorry. Okay, so there was one extension here, but let me just summarize. The AdGPI is a physical active learning. GPR AdGPI is boosting that in particular. We are further improving that for large molecules. In particular, we're interested in using also for the fragment-based approach, which I didn't have time to talk about. Let me just finally acknowledge my co-workers, in particular, Gunnar Schmitz and Dennis Aytuikin, who did much of the GPR work. And sorry for running over time, but I'm done.